We're going to shift gears now and talk about a different kind of calculus, calculus of parametric and polar defined functions. And you've probably seen polar defined functions before in your pre-calculus class. Hopefully you've seen it. If not, it's not really a big deal. We can definitely talk about the polar defined functions. But most of you probably have not seen parametrically defined functions before. These ones were not in the pre-calculus class. So if you have seen these before, that's good. But if you haven't, no big deal. We're going to go into them in pretty good detail here. Yeah, so you can read about what these are. I'm on 10.1 now. Suppose that x and y are both given as functions of a third variable t called a parameter by the equations x equals f of t and y equals g of t. Okay, so x equals f of t, y equals g of t. Right, so both x and y are actually functions of a third variable. And it's not always t. Sometimes they use theta, sometimes they use other stuff, but usually it's t. And t actually works pretty well because you can kind of view t as a time parameter. Yeah, and so it says as t varies, the point varies and traces out a curve, which we call a parametric curve. In general, the curve has those equations. T is usually bounded on some interval, and then there's an initial point and a terminal point. Basically, just whatever the starting t value is, that produces a point. Whatever the ending t value is, that produces another point. There's a curve that connects the 2 points. Okay, so again, I think on these ones, probably the best way to see what's happening is to just do a couple of examples. So again, here we've got x being defined in terms of t, y being defined in terms of t, and t being given some interval, in this case between -1 and 2. All right, so in general, kind of going back to thinking back to maybe your first couple of algebra classes and thinking about the graphs of algebraic functions, what did you do when you had no idea what the graph of a function was going to look like, but you wanted to find out? You didn't have a graphing calculator. You wanted to graph it by hand. What you normally would do is you just make a table of values and plot them. And then when you plot them, you can kind of follow along and connect all the dots, and you can kind of see what the curve looks like. And so we're going to do the same thing here. Only now we're going to make a table that has 3 columns instead of 2, because both x and y are going to be functions of this other variable t. Okay, so what we want to do is, again, pick some certain values for t. So I'm going to start with -1 since that's the smallest value, and we're just going to go up by intervals of 1/2. And this should give us a pretty good picture of what this is going to look like. Okay, so when t is -1, what is x? So I look at this, -1, plugging in -1 there and squaring it. 1 minus 1 is 0. So that's the x coordinate will be 0. When I plug in -1 for the y, I get -2 minus 1. So -2 minus 1 is -3, right? So the y is going to be -3. Stop me if I make a mistake. I'm going to do all the whole number ones because they're a bit easier to deal with here. So that's going to give us 1. Okay, now those half points, let me just use my calculator for these ones. So now what we have is a bunch of points. And so we can plot these points now. Now t is actually not going to show up on the graph. We're only graphing x and y here. Although t sort of is there in the background. We'll see how in just a second here. So when t is -1, the starting t value, we have a point, 0, -3, right? So 0, -3, right there. Then as t increases, we have a new point, 0.75 and -1.25, right? In fact, I'm going to try to exaggerate this a little bit better. I'm going to make this bigger. And then we go from there to 0.75, negative 1.25. So maybe about right there. Don't have to be too accurate here. We're just kind of getting a picture of what the graph's going to look like. Then 1, 0, then 0.75, 0.75, so about right there. Then 0, 1, so we're about right there. Then negative 1.25 and 0.75, so about right here. And then negative 3, 0, so about right there. So you can see that they seem to be following some path. So we can connect them. Everybody see what's going on there? And then, so that would be the graph of this parametric function on this interval. Okay? So I said that t is not showing up on the graph, but it really is, sort of like I said, in the background there. You kind of have to view this as a moving picture, as time, like you want to maybe picture a stopwatch that for some reason starts at t equals negative 1, and then it runs to t equals 2. So starting at negative 1, we start right there at that point. And then we, as time goes by, it moves along this path. Okay, so there's an arrow, a direction associated with this. So you might even want to be thinking of like a particle moving in time until it reaches its ending point. Okay, so thinking of this in motion is maybe a better way than just a static graph that we've been dealing with. All right, now on your calculator, you can actually do this. So if you have your TI calculator with you, go ahead and take it out now. I think I have my emulator here that I can share. So yeah, if you have your calculator, go ahead and try to follow along with what I'm doing. If you don't, you can get this emulator too. You guys see the emulator now? Wabbit EMU. You can just download that emulator, and that's what it looks like. Yeah, so the calculator will actually graph this parametrically defined functions. To do it, you just go to, you hit the mode button, hit mode, that's the button at the top there, and go to the fourth line there. You see how it says function, parametric, polar, and then sequence. That's what those mean. We're going to select parametric there, and then when we go to graph, just press the y equals button. Notice that when you press graph, it looks different than the regular function graphs, right? It's not the same as it was before. Well, that's because we're graphing a different kind of function. So 1 minus 1, okay, 1 minus, and then when you push that same button that produces the x, you see how it says x, t, theta, n? When you push that button, it's actually going to show up as a t now. So 1 minus t squared. Okay, and then we'll enter the y, the corresponding y that goes with that. 2t minus t squared. 2t minus t squared. Okay, so now we've entered our parametric function. Now we have to set our window so that we'll be able to see it. So I'm going to push window now, window, and then you see that now again the window even looks different. So ours starts at negative 1, so we're going to put in minus 1. And then it goes t max is, in this case, 2, so we're going to enter a 2 there. Now the t step, that basically, there's a sort of a trade-off there. The way the calculator actually does this is it sort of iterates. In fact, this is kind of like the Euler method, but really what it's doing is it's saying how much should I vary t before I enter the next point. And so if you make t very small, what that's going to do is it's going to sample a whole bunch. In fact, the smaller that you make t, the longer it's going to take to graph. If you make t too big, then what it's going to do is it's going to sample the points kind of far apart, and what you're going to get is like a bunch of sort of straight-looking jagged lines. It'll graph really quickly, but it won't look very nice. So there's a trade-off here. You don't want to make it too small because it'll take forever to graph, and you don't want to make it too big because then the graph will look very jagged and not very accurate. So I think about if I'm remembering, I think about 0.05 is a pretty good value for t. X min, this is just the normal, like what are we actually going to see on the graph? Well, from the graphs that I have on the whiteboard here, it seems like the smallest x value we're going to care about is probably -3. So I'm just going to make it -3. And the biggest x value we're going to care about is probably only 1, but I'll just make it a little bit bigger at 2. X scales, just where the tick marks are going to be. The y min value, it looks like we're going to go down to -3 also. I'll just use -3 there too. And then it seems that we'll go up to 1, but again, I'll probably just put that as 2. Put 2 there. And what else do we have here? Y scale. Yeah, that's it. Okay. And so now once you have that all set up, just hit the graph button and boom, there's the graph. And that looks pretty close to the thing that I put on the whiteboard. And let me just show you what I was talking about, like with this, the t step. Like, let's make that too big. Deliberately, we'll make it too big. Let's make it 0.5. Watch what happens when you graph it. Oh, it's even faster. It still looks pretty nice. Maybe even bigger would be obvious. Let's make it 1. Yeah, you see what happens when you make it too big? The graph looks pretty jagged. So, and just to show you what happens if you make it too small. Like, what if I make it 0.001 or something like that? See what I mean? Now it takes a really long time to figure out what the graph's going to look like. But that will produce the most accurate graph if you make it really tiny like that. And for that, you see what happens, right? We cancel that one. So I think like 0.05, like I said, I think it's a pretty good trade-off there. It graphs pretty quickly. Graph looks pretty accurate. All right, you see how that works? So in fact, from now on, when we do these graphs, I would just say, go ahead and use your calculator. It's really a pain to graph these things by hand because with regular algebraic functions that we've been seeing, we have a pretty good idea what they're going to look like just in general anyway. Like if I say, here's a parabola, cubic or square polynomial or cubic polynomial, we have an overall idea about what it's going to look like. With these parametric graphs, really, unless you played around with these a long time, it's pretty hard to tell what they're going to look like. So I would say, just rather than trying to mess with graphing them by hand, put it in your calculator or use Desmos. There's parametric Desmos graphers as well. So, all right, so that's what they look like. Example 2, again, this is another one that just says to sketch it. So I'm going to go ahead and use the calculator on that because I don't want to sketch it by hand. So let's switch this up and say t squared minus 3. All right, so now the window here, we're going to change it up a bit because it says that the t values are different, right? So -3 to 3. So we're going to make this -3 to 3. We'll keep that the same. And then the other values, I'm not really sure what this is going to look like. So for now, let's just do a kind of standard window of minus, what should we do? Let's try -3 to 3, I guess. And we'll see what it looks like. If it doesn't look good, then we'll try again. Okay, so we'll probably need to change things. It looks like our X window is good, but let's change our Y window a little bit. We'll go from -2 up to, I don't know, 5 maybe, 6. Let's try 6. Yeah, that's pretty good, right? That's showing us what we've got there. Looks like a sideways opening parabola. Okay. Now let's do the rest of the problem. It says, indicate with an arrow the direction in which the curve is tracing as t increases. So I think we can see that it's starting sort of at the bottom and then going up, starting at the bottom and going up that way, right? And in fact, our x max, we might want to change that just a little bit to see where it actually ends. Let's put that up to 5 and see what it does. And I'm going to change my y max a little bit as well. Yeah, it's ending somewhere off to the right there. I'm not exactly sure where. I guess if we plug in 3, we could probably see. It looks like y would be 5 and 6. Yeah, so it actually ends at 6. Cool, so there it is. Now let's finish the problem. This other part of the problem says we want to eliminate the parameter. So what does that mean? Okay, so eliminating the parameter, that just means that we want to get rid of the t and just put this back into its sort of normal function notation, just x's and y's. So what we'll find here is that we can actually do that. We can always change a regular Cartesian defined function into a parametric defined function, and vice versa. Any parametrically defined function, we can change it back into a regular Cartesian equation. So with this one, the method to do that varies depending on the function. If it's trig functions, there's usually kind of a different way to approach it. But with algebraic functions like this, it's actually not that bad to eliminate the parameter. In fact, it's fairly simple, especially if you've got an equation like this. If I'm trying to eliminate the parameter, I just need to get rid of the t. And I could do that by picking the easiest equation to solve for t, which in this case is this one, and get t is equal to y minus 2. And then I simply take that and plug it into the other equation, and boom, I've eliminated the parameter. So x is equal to y minus 2 squared minus 3. Now, if you look at that equation, and thinking back to your pre-calculus class, that looks like a parabola that is opening to the right, shifted. What is that minus 3 there going to do? Well, since it's an x equals, that shifts it 3 units to the left. So that's going to go 3 units to the left. That's its vertex. Oh, no, actually not, because it's also shifted this y minus 2. What's that going to do? That's going to shift it up 2 units. So that goes up 2. So its vertex is actually right there, and it's a rightward opening parabola. So it's going to do this, something like that. And if you compare that to the graph that just looked at on the calculator, it's the same, right? However, what we have to notice is that this graph, this equation, versus this set of parametric equations, do they tell us exactly the same thing? Do they tell us the same thing? Not quite, not quite. Because when you have that parameter t in there, that parameter t actually sort of, as we've noticed, it's kind of like a time parameter. And so when that's there, you kind of have to think of that this is actually maybe a particle, like I said before, in motion. And so really, we're not actually looking at the graph itself when we're talking about the parametric equation. We're not looking at the whole graph by itself. We're actually kind of thinking more about a particle that's moving along the graph. And it's got a direction associated with it. You see what I mean? So the parametric equation gives us a little bit more information than the Cartesian equation, right? The Cartesian equation is just the graph of the parabola, and that's it, right? There's nothing else to it, just the parabola. The parametric adds to that the sense of a particle perhaps moving along that path in a given direction. Okay, let's try another one with eliminating the parameter, but this one is a set of trig equations. We eliminate the parameter there in a little bit of a different way. It's not really that bad, just gotta kind of know how it works. So x is equal to 1/2 cosine theta, y is equal to 2 sine theta. These are our equations. In this case, theta is the parameter, not t. And here we're varying between 0 and pi. Okay, so the first one here is to eliminate the parameter and then find a Cartesian coordinate equation, then sketch it with a direction. Okay, so we'll first eliminate the parameter. I'll show you how that works first. The way to do this is to solve this left one just for cosine by itself. So I'm going to multiply this by 2. I get 2x is equal to cosine theta, and then divide this one by 2, so I'll get 1/2 y is equal to sine theta. And then what I'm going to do is just remember our most important trig identity. So trig identity, sine squared theta plus cosine squared theta is equal to 1. But since I've defined cosine theta to be equal to 2x and sine theta to be 1/2 y, what I can do is just replace those with, well, what they are, right? Sine theta is 1/2 y, so 1/2 y I'm going to put there, squared, plus cosine squared theta, 2x squared. So you see the kind of difference here. We're not solving this for theta like we did on the other one. On the other one, we solved for t and plugged that into the other equation. You could actually do that here, but it just ends up with having like signs of arc sines and stuff like that, stuff that we don't really want to deal with. So it's easiest just to take advantage of these trig identities to do these. Then we'll simplify this and we'll get 1/4 y squared plus 4 x squared is equal to 1. Now that you should probably recognize as, and I'm going to rewrite it a little bit differently. I'm going to write it as x squared over 1/4 plus y squared over 4, yeah, is equal to 1. And again, looking at it like that, do we recognize what that is? That should be, and we just saw it in the last section, right? That's an ellipse, right? That's an ellipse. And if you remember from your pre-calculus class, how do you determine like what direction this ellipse is opening? Like, right, I guess what the orientation of it is, right? Because you either have ellipses that are sort of elongated horizontally, or you have ones that are elongated vertically. Which one is this? Vertically elongated or horizontally? Another way to say that is what is its major axis? Is it along the y-axis, or is its major axis along the x-axis? Well, what you need to remember is that the one that has the bigger number on the bottom is the one that where the major axis is. So since 4 is bigger than 1/4, this thing is elongated vertically. And if you remember that the square root of those numbers in the denominator is the length of the axis. So remember that this is a squared, right? Or actually it might be b squared, I can't remember. But whichever one it is, the square root of it is 2, so that means that this thing is going up 2 units. So that'd be 2. And then this one is the square root of that is 1/2. And so this would be 1/2. And that'd be negative 1/2. So this is an ellipse elongated vertically, okay? Now, of course, the parametrically defined one is a little bit, kind of have to think of it a little bit differently, number one, because it has those bounds on theta, right? 0 to pi. And we want to be thinking of it as like something in motion, okay? So in fact, this is probably a good time to just show you that Desmos will do this as well. Now, Desmos does it even a little bit better than a calculator because it will actually show you the motion. If you can find, and it's pretty easy to find this too, all you would want to do is just Google, in fact, let me just show you. So to do that, you would just Google Desmos animated parametric. Desmos animated parametric with path. So here we go. This is the one we're going to look at. Okay, so they have all these examples here. I'm just going to alter this fourth example to match what we have in our problem here. X, we're going to have to change this to be sine of 1/2, or cosine, sorry, of a over 2. It's a little bit clunky to make this work, but this is the way that whoever programmed this did it. Okay, now we have to change this one also. This is the way that they forced this to work. So this has to be the same thing, except with a t. And we're going to change the t value to be starting at 0 and going to pi. And then I'll just press play, and you can see the one I don't really need to graph. There's one here I don't really need to graph, which is that one. That one in red is not necessary. I don't even know why they're graphing that one. The thing that we're looking at is really this black one here. Everybody see what's going on there? So that looks like, to me, the top half of an ellipse. And so if we were to increase the t value, you'd see that it would actually go all the way around the ellipse. In fact, we can do that. We can change this to 2 pi, and then change this to 2 pi also. And then try again and see what it does. See what it's going to do. It's going to go all the way around now. See the direction it's going to, right? As t increases, it's going in a counterclockwise pattern. Then for example 4, you can, we could do the same thing, just see what direction it's going to go. So in fact, let's just go ahead and do that. For this one, x equals 2 plus sine t. So let's change this to 2 plus sine a. And the second one, we'll change it to 1 plus 3 cosine A. And if we further change this to be the given values, like pi over 2 to pi, you can see what that would do. Pi over 2 to pi. Notice that that would just do the sort of bottom corner of that ellipse. So to answer the question, describe the motion of the particle. As t increases, it's going to sort of trace along that bottom right quadrant, I guess, of that ellipse. All right, so now, just as we could take a parametrically defined equation and put it into Cartesian form, you can also go the other way. You can start out with a Cartesian defined function and put it into parametric form. In other words, parameterize it. So basically any any Cartesian equation, as in any equation that we're familiar with from, all our other math classes, y equals whatever, those can all be turned into parametric equations by parameterizing them, okay? And so that's what we'll look at now. In fact, when you get to Cal 3, this idea of parameterizing things is really going to be a big deal, because a lot of this stuff in three-dimensional parametric equations, oftentimes it's just easier to have it as a parametric equation than a Cartesian defined function. So get used to this. This is very important for Calculus 3. All right, and so yeah, so you'll see in Cal 3 what this is going to be doing is like you'll have a curve actually moving through space as time goes by. So you have to graph it in 3 dimensions. It's a bit harder to do that. There actually are 3-dimensional parametric graphers though out there. I don't think Desmos does it, but I think, what is it, GeoGebra does that? Is that right, Michael?
I think GeoGebra has some 3D stuff, but I haven't really figured it out.
Yeah, I think I messed with that when I taught Cal 3 the last time. But yeah, they are out there. You can graph 3-dimensional parametric equations. All right, so we want this. We have a regular defined function. And again, this would just be, if we were to graph this thing, this would be an ellipse. And we're trying, but it would just be an ellipse, like static sitting there, right? But what we're going to do here is parameterize it so that we'll have a particle moving along this path, and we'll also be able to decide which direction it's going and where it begins as well. And so how are we going to do that? Well, parameterizing stuff like this is a little bit harder than going in the other direction. What you have to do is, again, make use of that, this sine squared theta plus cosine squared theta equals 1. That's the key for this here. So what we're going to do is let x equal, we're going to let x minus 2 equal 3, and I don't know, we should do sine or cosine. I'll just say cosine first. And then we're going to let y equal 3 sine theta. Okay. So why did I do that? Why did I what's the thinking behind this? Well, for one, I'm looking at what's on the right side there, right? That is like the radius, I guess, of this. In fact, this would be a circle, I think. So this would be the radius of that circle.
Yeah, it's a shifted circle.
Right, so it's a shifted circle, shifted 2 units to the right, I guess, and radius 3. And so what we do is we just take whatever this thing is being squared, set it equal to the square root of that, either sine or cosine theta, and then you take this thing and set it equal, just the square root of it, set it equal to, again, square root of that, the other trig function of theta. So you're going to make one of them sine and one of them cosine. Now, you can switch those around too. You can make one sine and one cosine, depending on where you want that starting point to be. So just looking at the way I've done it, does this match the starting point? And if it doesn't, then we can always switch it. So again, I'm looking at that, 2, 3. Does this thing start at 2, 3 if I start t at 0? So think about what happens when t is 0. If t is 0, then I'm going to have cosine 0 there, which is 1, right? So that's going to be 3 plus 2 is 5. That's not 2, right? And so I've chosen the wrong thing here, which is fine. That all that means is that I should just switch this, and instead of cosine here and sine here, I should probably just do it the other way. So let's see what happens if we do that. Is that going to fix it? So if I put sine here and cosine here, what happens then? Well, let's see. X is equal to, now the sine of 0 is 0, so that is going to give me a 2. And then if I plug in cosine here of 0 is 1, that is going to give me the 3 right there. So that's the one I want. Now, again, you might want to just wonder, or you might be wondering, like, why is this working? Why does this do the parameterization? This works because if you do this, look what happens when you, just to check to see if this is actually a good parameterization. If x minus 2 is 3 sine theta, then what I can do is replace it, right? I can replace this, the x minus 2, with 3 sine theta. And then it becomes squared. And then the y is that. I can replace that with the 3 cosine theta, you see? And so that would be 3 cosine theta. And then that would be squared. And supposedly this is supposed to be equal 9. If I have chosen a good parameterization here, then I will end up with a true statement after I make this little substitution. And it seems that I do, right? Because this becomes 9 sine squared theta plus 9 cosine squared theta equals 9. Is that true? I think it is, because look what happens when you factor the 9 out. You're left with sine squared plus cosine squared, and we know what that is, right? That's just 1, so we get 9 equals 9. So this is a good parameterization, okay? So if you see a situation like this where it's some quantity x minus something or plus something squared plus some other quantity of x squared, or y squared, equals to something, this is the way that you'll do the parameterization. Okay, so the first thing will be equal to r sine theta, and the other one will be equal to r cosine theta, where this is r squared right here. All right, so there we go. That's the parameterization. This is the one that, this is actually going to start it in the correct place, as we just saw, plugging in 0 for theta here. Oh, I should be using t's instead of thetas. Oh well. I'm just going to change this to theta. How about that? I guess they wanted us to do this with t's, but that's okay. Theta's a t. It doesn't really matter. All right, so with all that in mind, now the last thing that they were wanting to happen here is that this is going clockwise, right? Clockwise. So is it going to go clockwise? Now the best way to check that is to actually just put it into your calculator and see, does this produce something that goes in a clockwise direction? So we have like 5 minutes left. I think that probably is barely enough time to do this, but let me just show you how we would check to see if it goes clockwise or not. So we'll come back to our calculator. We'll enter x equals 2 plus 3 sine t. 2 plus 3 sine t. 3 cosine t. And then we'll just change our window. Okay, look what it's doing, clockwise, right? So that's good. Now, what if it wasn't going in the right direction? How would we reverse the direction? Well, coming back to the, in fact, without going back to the whiteboard, remember that I chose the x to be equal to 3 sine theta or 3 cosine theta, right? But then that gets squared in the function, right? So it doesn't matter whether I've chosen a negative or a positive. So a way to sort of fix this is to go to the sign one, the one that has a sign in it, and just change the sign, S-I-G-N. Like, watch what happens when I change that to a minus instead of a plus. And then let's graph it again. Look what it's doing now. It's going counterclockwise, you see? Everybody got that? I'll go back to the whiteboard and reiterate, but if you notice, that's what changed the direction, right? Changing that to a plus, it goes clockwise. Having it a minus, it went counterclockwise. So notice the reason it's okay to just randomly switch that is because this is being squared, right? So whether I made this minus or plus, or even that one minus, it doesn't really matter because squaring it is going to make it positive, and it's still going to satisfy this equation here, you see? So it's still a acceptable parameterization. Now, which one would you want to make negative? I said the one you want to make negative is the one that has the sign in it. That's the one we would choose to change the direction. Why? Because if we put the cosine one, that would then change the starting point, because cosine of 0 is not 0, right? So the one that you want to change is the one that has the sign with it, SIN sign. You want to change the SIGN sign of the one that has the SIN sign on it. Okay, does that make sense? That's what changes the direction anyway.